All right, so we are going to go through this set of practice problems, constant velocity motion. So for the first four, this top chunk right here, what we want to do is for each of the following graphs, determine the initial position and the velocity of the object, and then we'll write an equation that describes the motion of the object as a function of time. So before we start, what I'd like to do is talk about that equation that describes the motion of the object as a function of time. That's very important. So, in general, when we're looking at graphs, and in general, a graph is going to be a y-axis and an x-axis, and we get a line, and that line has a slope. We generally use m for the slope. And that's our y-intercept. We use b for that. And the equation that describes this line is y equals mx plus b. That's the equation that describes our line. But what we've been doing is making our graphs not y, but position. And so instead of a y here, we're going to write position. And instead of the x-axis, it's time. So instead of writing down x-axis, we're going to actually write down what's on the x-axis. And we said for a position versus time graph, that slope is equal to the velocity. And so instead of writing m for the slope, we're going to write velocity, because the slope of a position versus time graph is velocity. And instead of calling our y-intercept b, since that's the position graph, that's going to be our initial position. So with this little equation, we can do all the same things that we did with y equals mx plus b. We're just going to call everything by the proper name. So our y values are all x for position, my slope is the velocity, all my x values are time, and my y-intercept is the initial position. So this is the equation that describes motion. So for each of these problems, what we're going to do is find the initial position. We'll just plug it in right there. And then we will find velocity, which is just finding the slope, and we'll plug it in right there. So for number one, looking at it, my initial position is right there, and my initial position is -3 meters. So I have that piece of information. What I need to do now is find the slope of my line. So to find slope, or to find the velocity, whichever thing you think is easier, I think finding the velocity is easier. So we're going to do delta x over t. So if we start here as our x position, that's our initial position. And if we end over here, we go from -3 to 2. Well, going from -3 to 2 means that my displacement was 5 meters. And it takes 10 seconds worth of time. So my velocity is 5 meters per second. That's going to be my velocity. And this is how we're going to find our velocity every time. Now, once we have that, it's time to write the equation that describes that motion. Looking at this motion, it's going to be final position equals velocity 5 meters per second times the time plus the initial position, which is -3 meters. So x equals 5 meters per second times time minus 3 meters. Any one of those two is just fine. But that's how we're going to find the initial position and the velocity and write out our equation. For the second one, looking at it, my initial position, x0, is 4 meters. And then to find the velocity, we're going to do the displacement over the time again. If we start here in our displacement and we end here, we go from 4 all the way down to -4. So my displacement is -8, because that's how far it is from 4 to -4, over the time. And that whole thing takes 6 seconds. So my velocity comes out to be -1.33 meters per second. So if I'm going to write out that equation, it's going to be x is equal to -1.33 meters per second times the time plus 4 meters. That's our equation for this line. For number 3, same thing. That's my initial position. x0 is equal to 2.5 meters, and it's 2.5 because it's half of 5. And then to find my velocity, it's delta x over the time. So if we start at 2.5 and end over here at 7.5, the distance between 2.5 and 7.5 is my displacement. So we have 5 meters over the total time that it takes to do that, 10 seconds. So that velocity is 0.5 meters per second. And my equation comes out to be x is equal to 0.5 meters per second times time plus 2.5 meters. Just noticed I made a mistake here. This is all 0.5 meters per second. 0.5 meters per second. Apologies for that. Number 4, same deal. And if you want to, for any of these problems, it's a great idea to pause before I work it out so that you can work it out for yourself. So for number 4, we have an initial position of 10 meters. Our velocity is going to be the change in position over the change in time. We start here at 10. We end down here where my final position is 5. So the distance between those two is -5 meters. That's what happens when that points down. And then the time, we go from 0 to 20. So the time is 20 seconds. A little off screen. -5 meters over 20 seconds. That makes our velocity -0.25 meters per second. And then we need to write out our formula. So our formula is going to be x is equal to -0.25 meters per second times the time plus 10 meters. So that's our top chunk of problems. For the bottom chunk, we're going to graph this thing given the initial position and the velocity. So it tells me in number 5 that my initial position is 1 meter. So we start here. And that my velocity is 2 meters per second. So there are 2 ways you could do it. The easy way is to count over in terms of your scale. That means that every 1 second we go 2 meters. So 1 second takes me up to 3 meters. Another 1 second takes me up 2 more meters to 5. That's one way that we could do that. The other thing that we could do is to say, well, I've got this equation where I've got x is equal to velocity times time plus the initial position. So let's plug some random numbers in. I'll just use 2 seconds. That's going to be my time. So I've got 2 meters per second times 2 seconds plus 1 meter. That gives me 5 meters. So I know my initial position is 3, and my position at 2 seconds is 5 meters. And so with those 2 points, I can draw my line. I'm going to do this way all the way through this worksheet. but you could always count according to the scale on your graph if you wanted to. So for number 6, my initial position is -1 meter, and my velocity is 2 meters per second. So my final position is going to be 2 meters per second, and for this one, again, I think I'm going to choose a time of 2 seconds, so times 2 seconds, plus my initial position of -1. So I'm going to have 4 minus 1. My final position, or my position at 2 seconds, is going to be 3 meters. So at 2 seconds, we're at 3 meters. And that's our line. For this third one, number 7, the initial position is -10 meters. The velocity is 5 meters per second. So we have x is equal to velocity times time plus x0. So x is equal to, x is equal to 5 meters per second times, I'll go with 2 seconds again, 2 seconds plus -10. So that makes my position 10 minus 10, or 0 meters. So my position is going to be 0 meters. And that's my graph. If you wanted to count for this one, it's a little bit tricky, but it's 5 meters per second. So every second, we're going to go 5 meters up. So 1 second, and then 5 meters up is actually right here because of the scale. And 1 second over, and 5 meters up, and 1 second over, and 5 meters up. It's the same line, but when you count like that, if you count like that, you have to be aware of the scale. For the last one, my initial position is 5 kilometers, and that's my speed. So the position is equal to velocity times time plus the initial position. So it's equal to -0.25 meters per second. And I think I'm going to choose 10 seconds this time. It does not matter what time you choose, plus my initial position of 5. So -0.25 times 10 is -2.5 meters plus 5 meters. So my final position is +2.5 meters. That's right along this line. So at 10 seconds, if I'm at +2.5 meters, I'm right there. And then that's my line. All right, the next part of the worksheet, number 9, I have a pool ball rolling along a pool table with a velocity of 0.5. At the end of the table, 5 meters from where it began, the ball strikes the edge of the table and comes to a stop. This is the place where I want us to use the guess method. I'm going to write it out here. G-U-E-S-S. G is for our given information. U is for our unknown information. E is for the equation that we will use. S is for substitute your numbers. And the other S is for solve. Now, right now we only really have one equation that we're going to use. So the guess method is going to be a little simplistic for what's going on, and that's okay. But we're going to want to use this guess method throughout the class, and I want us to be used to what it looks like, and I want us to be used to how to do it. So, using the guess method when we need to find a value. So if we look at what's going on, for the first 5 meters, my velocity, this would be my givens, my velocity is 0.5 meters per second. My change in position, because we're going 5 meters away, is 5 meters. And if I want to graph that, I need to know where to stop. So that makes my unknown time. Now, the equation that's going to help me find this is velocity is change in position over time. So we want to put some numbers into this, so we'll substitute in a number, both numbers that we have. I know that the velocity is 0.5 meters per second, and that's equal to the delta x of 5 meters divided by the time that we don't know. Now, time is in the denominator. When we're solving for something, we want that thing, so in this case time, to be on top or in the numerator and by itself. So we're going to multiply both sides of this equation by t. That makes these t's cross out. So we have t times 0.5 is equal to 5. If I want to solve for t, it needs to be by itself. In order to do that, I'm going to divide both sides by 0.5. So that goes away. And my time here comes out to be 10 seconds. So what that tells me is that after 10 seconds, we go from 0 meters to 5 meters. And then it says it strikes the edge and comes to a stop. So we know that when we're stopped, the velocity is equal to 0 and we have no more speed, and so we have a 0 slope or a horizontal line on our position versus time graph. At the same time, we're going to want to graph that thing over here for velocity versus time. So after 10 seconds, we get a change in our velocity. We start off with a velocity of 0.5 meters per second, and we end with a velocity of 0. So we have that nice little stair-step graph from 0.5 meters per second to 0. Number 10, we have 3 different motions that happen. The first one, we have the man walking towards the bus stop 100 meters away at a constant velocity, and he reaches the bus stop in 200 seconds. So the first chunk of our motion is from his house towards the bus stop. The second chunk is that once he's at the bus stop, he's going to sit for 500 seconds and wait for the bus. Our third chunk is he realizes he forgot something and he runs home with a speed of 2 meters per second. So we have 3 different chunks. What I want to do is list out all my given stuff for each of these 3 chunks of motion. So for my first bit of motion, the man walks towards the bus stop 100 meters away. So I know that the man's displacement in this chunk of motion is 100 meters. And I know that it takes him 200 seconds to reach the bus stop. What I don't know for this is the velocity. That's my unknown. For the next chunk, once at the bus stop, he sits for 500 seconds. Well, what that tells me for this one is that the velocity is 0. When he's sitting, he has a velocity of 0 meters per second. And his displacement is unknown. And the time, I did that backwards. So he's sitting for 0 meters per second for a time of 500 seconds. So our unknown there is his change in position. And then for the last one, our given, he's going to run back home. So our delta x is 100 meters, but it's back home. He's going in the opposite direction, so it's negative 100 meters. And he does that with a speed of 2 meters per second. And what we don't know here is the time. Our unknown in this case is the time. So what we need to do is find the unknown in each one of these cases. So here it's the velocity. I know that velocity is displacement over time. So it's going to be 100 meters over 200 seconds. So the velocity here is 0.5 meters per second. That's what we have for the first chunk of information. For the second one, we want to find delta x. So our equation for that is velocity is equal to delta x over time. So our velocity 0 is equal to delta x over time. The only way for this to work, and if we're sitting still, the only way that happens is if the delta x is 0. That's what it means to sit still. It's our last piece there. And for this one, we want time. We want to give ourselves some room. So our equation here is that velocity is displacement over time. So when we substitute our things, we get 2 meters per second is equal to our displacement over our time. That needs to be a -2. Well, because we're walking backwards. So in order to solve for time, we have to multiply both sides by time. So we have t times 2 is equal to 100. So we'll divide both sides by 2, and we'll get that t is equal to 50 seconds. So these are all of our pieces of information. Now we can graph it. So for our first chunk, first off, our total time is 200 plus 500 plus 50 seconds. That's going to be 750 seconds. So if we go through and we do this, it's 100 every 2 blocks. 200, 300, 400, 500, 600, 700, and then that last one would be 750. So from 0 seconds to 200 seconds, 0 seconds to 200 seconds, we go 100 meters. That's what we have for our position. From 0 seconds to 200 seconds, we go 100. In the next 500 seconds, we don't go anywhere. There's no change in our displacement. So we stay for the next 500 seconds at 100 meters. And then in the next 50 seconds, we go back. So our graph looks like first section 0 to 100 in 200 seconds. Second section 0 to 0, well 100 to 100 in 500 seconds because we're not going anywhere. And then our last chunk, we're going from 100 back down to 0, that's that negative thing, in 50 seconds. So there's our graph for that motion. Then we need to do the velocity. We have the same breakdown of time, so 100, 200, 300, 400, 500, 600, 700, and then 750 seconds. So for our velocity, we start off with a velocity of 0.5 meters per second for 200 seconds. And then we stay at rest for 500 seconds. And we end with a velocity of -2 meters per second for the last 50 seconds.